Hello everyone and welcome to my continued exploration of MECO Rocket Simulator, early access game slash sim available on Steam. And in the first video I put together a pressure fed little nitrogen thruster, and this time we're going further. We have to deal with valves now, and we know how tricky valves are. Today we break something on purpose. Well, that's a good introduction to valves. Snap a valve open, watch the pressure spike, then smooth it out. It notes that even at 0% open, the sim lets the valve leak a little and keeps things numerically stable. Real seals are rarely perfect anyway. So, interesting. So the current objective is on the model page. We're going to duplicate my first model, so that one. Right? So this thing. Insert a node internal. So, not what I wanted. Delete. Escape. Okay, escape is what you use. Node internal. Between the branch and the mode outlet. Okay, so here. Okay, well, now we've got it. It doesn't do the thing where in other programs with little nodes like this, if you hover something over it, it'll automatically try and join them or put it in the middle. Well, looks like that doesn't do that, so I guess maybe that's why. Okay, so rewire the branch, disconnected from node outlet, done, and connected it to this. And then node internal geometry. The length is 1 cm, cross section is a circle, and radius is 1 cm. Okay. Add a branch valve. Okay, so in order to connect it to the outlet, we need this branch valve. I wish it would explain what the node internal represents. I mean, so it says add a valve with a transition control, trigger a pressure spike, and then tame it. But really, we need a sense of what these actually represent a little bit better. So that would be a good idea. All right, we have connected that. Now the valve geometry. The length 50 centimeters. That's a pretty long valve. Passage roughness 1.5 microns, right? And there we go. Add control parameter transition, set parameter type to valve open. Transition. And so we can hook that up, presumably. And this is actually how we control the valve. Start 0.1. Well, that's our little leakage, apparently. And valve open is 100. Transition takes 1,000th of a second. And the midpoint time is when it happens, I suppose. 1 millisecond transition, shut to wide open faster than you can think about it. Okay, max time 1 second. Shouldn't we have a monitor? Make sure the simulator drawer is open. Okay, well, run. Okay, so it sort of does a wobble, and then we hit 0.5 seconds, and then the valve is open. Water hammer. The fluid column slamming into the southern opening. Chart static pressure at the node internal to see how hard it actually hits. Okay. Static pressure. Whoa, it's all over the place. Oh, I wanted a new chart, that's why. Okay, there we go. Well, just the start of it, there's a lot of oscillating pressures, and then there's a lot more here too. Okay, open the branch in the component editor. Is it this one? I suppose. Okay, there's a fittings drop down and it wants tank baffles. They add resistance and damping. And we want to run it again. And so suddenly it does this instead. So much more tame oscillations. And then we can change the transition duration. Was it? It wasn't here. It was this one. 0.1. Okay, then it's smoother. Though it's interesting. Why does it start to seem to do something? The transition duration is 0.1 seconds. The midpoint time is 0.5 seconds. But it sure seems like it does some... It ends by 0.4 seconds or something. It's or pretty close to ending at 0.4 seconds. So I don't quite get why it starts so early instead of going from 0.4 to 0.5, this transition. Settle into a smooth ramp, no spike, no oscillation. Open the valve slowly and the fluid has time to accelerate with it. Small hammer at T0. That's because we slammed the pressure to 3 bar instantly. Probably we'll have to fix that too. But still, I don't understand the timing of this. Why does it start when it does? When apparently we said that we were going to have the... I mean, it's open a little bit, so we do see a sort of trickle thing going, but why does it start there to do its turn when it doesn't seem like that's when it should, given the duration? I don't know. Okay. Well, that's valve. Well, not quite as exciting as I was hoping for. Combustion. Next up is combustion. Surely things will explode there. The combustion catastrophe. All right, so combustion catastrophe. So it's promising problems. I didn't feel like there was nearly as many problems with the valves as I was hoping for. But build a gas generator with oxidizer and fuel feed lines. Oh, there's just the gas generator, or do you mean gas generator engine? To learn combustion fundamentals. Time to light something on fire. The combustion chamber modeled on the SpaceX Merlin 1D, and it gives the stats of the Merlin 1D. I presume that's the sea level thrust. And so LOX and RP1 propellants, similar oxidizer fuel ratio, and the physics is the physics. Okay, watch it run, create the fuel feed lines. A little bit simplified. A simplified model. Real engines use precision injectors for mixing. We'll get to injector design in later missions. I'm not sure whether it's got to be super accurate injector design, but we will see. But yeah, I think they meant a gas generator engine, not just the gas generator. New model. Oxidizer line first. LOX brings oxygen. So we add node inlet, and we want it to be named oxidizer inlet. And this is oxygen. Add a branch valve. And they want 1 meter length. Seems long to me, but okay, it doesn't want any fittings yet. But we sort of know that fittings are a thing that we might want. Okay, control parameter. And there's not a control parameter transition. I wish they would explain exactly what the difference is, but of course it allows you to do different parameter types. Oh, it wanted to be connected to the oxidizer inlet, not that. So, okay, no. Okay. Okay, can I cross that? Yeah. Getting rid of connections is a little bit different. I know how it's done in Blender, but I'm not sure that that's how it's done here. And in fact, mostly it's not. So there is a way to do a cross cut of a connection in Blender in order to sever a connection on the nodes, but that's not how you do it here. Okay, so now we do pressure, and we want 120 bar. The 5.6 centimeter radius is deliberately oversized at full valve open. That geometry pushes the mixture hot and oxidizer rich. That's on purpose. Use multi-select to copy components. Okay, so we're going to create a fuel line. Open the menu. See, for something else, we would just do control and drag or shift and drag to select multiple components. But it looks like we have to click on that and do start multi-select. Click copy from the pop-up menu. Was there a pop-up menu? Can I do Control C, Control V? Well, I can do Control C, Control V. It's fine. I don't want the pop-up menu. It's fine. At least that works. Okay, so we want fuel inlet. And oops. I wonder why it didn't have me copy the oxidizer branch and turn it into a fuel branch. Okay, circle, radius 2.5. Number of channels, I assume one. Oh, is this? Well, it said add a branch, so this is a branch. And 1.5. This one didn't have as many options as this one. Did I go with the wrong kind of branch? Well, yeah, on oxidizer branch, it asked me to add a branch valve. But on this one, it asked me to add a branch. And that means this has more parameters in it, but I'm not too sure why we have these two things. Okay, with both valves open, the geometry alone runs the mix oxidizer rich. That's the problem you'll tune out at the end. Well, I mean, part of it, it's not just oxidizer rich. The ratio between the fuel and oxidizer, as we knew right from the start, I thought it mentioned, was 2.36. So if it's that kind of ratio, you need a wider pipe for the oxidizer, of course. I'm not too sure that the pressure should be the same for both of them, all things considered, but anyway. Combustion chamber itself, the place that they meet, yeah. Add mode or node gas generator. Well, that's one place the two meet. I mean, I guess it's defining gas generator as the thrust chamber. Oh, they both get connected to the same port. Add a valve transition so the oxidizer eases in instead of slamming open. Yeah, well, we're nothing near a real Merlin ignition system, but okay. Control parameter transition. So this branch that we have over here does not allow for that connection. We can't use this control parameter transition for it. Okay. Merlin 1D ignites with TTEB, triethyl aluminum, triethyl borane, the green flash you see at liftoff. Here, the ignition's automatic. Oh well. Time to build the downstream side, where the hot gas actually goes. First piece is the chamber section off the gas generator. Oh, okay. Now, okay, so there's a real chamber, apparently. Maybe. Add a branch gas. Rename it chamber branch. Oops. Length 30. Cross section circle. Radius 15. Channel 1. And then there's a node gas internal. And again, I would like to know exactly what the functions of... I mean, we're learning the functions in terms of where it tells us to place them, but not why they exist fundamentally. Why are they a thing that needs to happen? Okay, this needs to be throat junction. So it's still... The gas generator is... Okay, so... how the engine is supposed to work is that there is a gas generator that runs the turbo pumps to feed the propellant into the combustion chamber, right? That's what the gas generator is. The gas generator is not the combustion. Well, you could call the combustion chamber a gas generator, I suppose, but technically when we say gas generator engine, we mean that there's this little gas generator that takes some of the propellant and combusts it so that that can run the turbo pumps. But you don't have turbo pumps right now. We're assuming it's a completely pressure-fed situation. And so it's sort of a misuse of the term gas generator here, but I guess the term gas generator here is being used as anything that injects the fuel and oxidizer together. So, okay. We'll handle that later. Okay, we are all connected like that. So then we have a throat branch. And they want this to be 5 cm, a circle, radius 12.3, and 1 channel. And then finally the outlet. And then we have to tell it that we are looking for 1 atmosphere of pressure at the outlet. So control parameter. We're skipping the nozzle expansion section this time. Proper nozzle modeling and ejector design both show up in later missions. Okay, now we get to run the simulator. Unable to run model. Component, what? Too quick. Required properly. Okay, property length. Must have missed that. Okay. It let me go past. I thought, okay, well, sort of was happy with it, but fine. Well, we need some graphs, don't we? Here, stagnation temperature. And I want stagnation pressure on the same chart. Well, it's got what we had. So we see that the pressure ultimately went up like that to 117 bar. And the temperature went up to 3,948 Kelvin. pretty steadily. And we want the mass flow rate as well. That had a pretty high mass flow rate early, and then it stabilized down here. Wonder why that is exactly. And it wants the max time to be 1.3. I think the valve is at 100%, so we have all that. We didn't even need baffles or anything. Okay, so we're too hot. Well past what turbine blades or chamber walls survive. The oxidizer line is flooding the mix. Something has to give. If both pressure set points are the same, 120 bar, the oxidizer fuel ratio comes down to which side can deliver more mass flow, and that's set by each line's flow resistance and the fluid itself, not the set point. Watch the charts to see how mixture ratio drives temperature and pressure. The ideal reference is 2.36 oxidizer fuel ratio. Once the sim finishes, hover over the lines to read. Yeah, I've already been doing that. The flat bit at the tail is your steady state. Yeah, got that. Okay, so then we have to try for Merlin-like conditions. So we're supposed to control this valve so that it doesn't have, well, not that low. It says 75. Wants to keep the same inlet pressures and then run it. So the presumption is that this brings us closer to what Merlin actually has, and the temperature is now 3,500. Of course, without any cooling, that'd still bust the engine. But I guess it's within the requirements. And the mass flow rate stabilizes at 296.4, and it wanted 295, but it seems to be willing to take that. And well, we don't really know our oxidizer fuel ratio right now. Let's see. Okay, add a chart. Let's get the mass flow rate for both of them. I don't know why this one's pink, but that's fine. What it's interesting, well, it's because we have this control parameter on the oxygen that the oxidizer one goes up smoothly like this, but then the fuel one spikes and then goes down, which is why on our mass flow rate we have a spike early and it goes down. So if we had this control parameter on the fuel one as well, it'd be smoothly going up as well. And we see that the oxidizer, in terms of mass, the oxidizer is twice the fuel. So it's not 2.36, it's more like 2, just 2. So we actually want more. So in theory, if we wanted to get the number, we would increase this, right? Now it's a little bit closer. But the temperature has gone up. I would like to know my performance. I forget how to do that. We can get outlet pressure. Compute nozzle thrust. Well, that's what I want. Oh, I can't add another chart, it looks like. It also doesn't let me get rid of this one. It doesn't, oh, now it's okay. Maybe. Can I add another one? Okay, now it's good. Chart 6 though, suddenly. Okay, so at this throat branch, we can compute nozzle thrust. Greater than Mach 1. Well, if this is the throat junction, I feel like it should be greater than Mach 1. Well, should we increase the length then of the chamber? Oops. Because we're not getting to Mach 1. Let me get rid of this. That doesn't seem likely if we are getting Well, I don't know. I guess maybe it's possible. We're only measuring the mass flow rate and the temperature. Okay, so compute nozzle still needs to be greater than Mach 1. Maybe we should reduce the radius. I don't know what the throat junction is doing, to be honest. Chamber branch doesn't seem to change a whole lot. Yep, doesn't seem to change a whole lot. The length that I have here. I guess maybe I can add another throat junction and then a throat branch. I'll tighten up the radius here. Oh, the same radius here. 10 centimeters, huh? That seems big. That's 15 for the chamber. And gonna try and compute the thrust again. Oh gosh. Missing required sampler outputs. Pressure, temperature, R gamma. Huh. So if I put a second one here, it doesn't like it. Oh, error invoking remote method, nozzle get sample, Mach exit needs to be more than 1.001. Wow, that's the same error as we had before. So this is interesting. I mean, I can't seem to get the performance of my engine here. But anyway, maybe I should back off of this. Combustion pressure can't go above feed pressure. One would hope so. Alright, well, that's all they have for the mission, though. So, to some extent, okay, we've got combustion now. But on the other hand, I'm dissatisfied because I can't get my stats. I can't figure out what thrust is producing. And, you know, the fact that I've tweaked the mass flow rates a little bit to get closer to the oxidizer fuel ratio, I can't see the real net effect of that, whether it's improving the efficiency. And they say it goes up to 85. Well, let's just try 85. That's a little bit closer to the ideal oxidizer fuel ratio that we would be looking for, but it is quite hot. Is there any other way I could get the performance? It doesn't seem so. The only place to get the performance is this branch. Oh well, okay, complete mission. Okay, and later missions come back to injector design. Hopefully also turbo pumps happen. We have learned how to select and copy paste and then do a mixture ratio in theory. And then some stuff about valve timing. But there's a lot more to figure out, and there are more missions. The next one is how to keep the throat wall cool, which is very important. But this time we did valves and combustion. So that'll do it for this video, and I'll continue to see what this MECO rocket simulator has to offer. So with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.